Year 11, this is my last shot at explaining limiting excess questions for the prelim course. But first, a couple of things I noticed in experiment 8-9 I want to clarify. The first one is dissociation or dissolution of salts writing equations. If you're asked to write an equation for dissolving a salt, don't put water in the equation. You don't need to. So for example, if you want to write the dissociation equation or dissolution equation of sodium chloride, all you've got to do is say sodium chloride aqueous turns into 1 sodium ion and 1 chloride ion. Similarly, if you're asked for the dissociation equation of calcium nitrate, all you've got to write is calcium nitrate aqueous turns into 1 calcium ion and 2 nitrate ions. That's all you've got to do. So as a practice one, have a go at this. Write the dissociation equation of iron 3 sulfate. If you've done it and you've done it right, you'll know. If you're not sure though, that means you've got to check with someone to find out if you're right. So I'm not going to give you the answer for that one. See if you can figure it out for yourselves. The next thing that came up in the experiment was making a precipitate. There were some questions that said, what solutions would you mix to make this certain precipitate? So for an example here, what solutions would you mix to make a precipitate of lead sulfate? So you've got to think to yourself, I've got to mix 2 soluble salts. So one of them must be lead something, the other one must be something sulfate. And what 2 things can I put there in those gaps to make 2 soluble salts that will mix together to make my precipitated lead sulfate? Well, the easiest thing to do is to think what is always soluble. Now, group 1 metal cations are always soluble, and nitrate anions are always soluble. So when we're looking for these 2 mystery things, choose from those 2 things there. So we can mix together, for example, lead nitrate, because the lead nitrate will always be soluble. Other things, sodium sulfate, sodium is group 1, sodium sulfate is always soluble. Mix lead nitrate and sodium sulfate salts together, you end up with lead sulfate as a precipitate. So to see if you get that, see if you can figure out what 2 solutions to mix together to make silver phosphate. If you know you've got it right, you'll just know. If you're not sure, check with someone and see if you're right. Now let's move along to limiting excess questions. This all comes from worksheet A, which was in your Water Focus 3-4 booklet. I'm going to suggest the following. You can either do this with me as I'm going and pause it every now and then and try it yourselves, or listen to the whole explanation, then put this away and try the question for yourselves to see if you can get it right, because the only way to be sure you understand is if you can do this stuff independently. If you're constantly listening to my words and just copying down the stuff on the screen, you're not actually learning. You've got to be able to do this on your own. That's the way to test if you really know what's going on. So let's have a look at this question. We've got 27 grams of lead nitrate dissolved in 1,000 mils or a litre of water, and that was added to 2 litres or 2,000 mils of 0.5 mole per litre potassium iodide. And we've got a whole lot of series of things there, which the chemical equation, which one's excess limiting, what mass of precipitate is produced, and then the concentrations of all the ions at the end. So how do we solve these sort of questions? First thing, get your equations done. So pause it now if you want to and write down the chemical equation and also the net ionic equation for this reaction. Okay, so if you paused, you should be able to check this now. If you're just listening on, that's fine. There's the chemical equation. I'm not going to explain it to you. You should be able to figure that out for yourselves. And there's the net ionic equation. Noting in the net ionic equation, it is the, here we go, it is the precipitate that ends up in the reaction, and therefore the only 2 ions here are the ions that actually react in the net ionic equation. And the next thing is to look at the starting moles. I'm not sure why that jumped forward so fast, but basically find the moles of the first thing, lead nitrate, and that's just mass of a molar mass, and you should get 0.0815. But because it's a question involving ions at the end here, I'm also going to suggest you also calculate the concentration of both ions, lead ions and the nitrate ions. And when you do that, you should be able to see that, well, the lead ions, there's 1 lead in lead nitrate, and therefore you should get 0.0185 moles of lead. But there's 2 nitrates in lead nitrate, and therefore you get twice as much nitrate, or 0.163 moles of nitrate at the start of the reaction. By the same thing, we can figure out the moles of potassium iodide, which is just concentration times volume, or 2 times 0.5 gives me 1 mole of potassium iodide. And same thing, what's the concentration, or sorry, what's the moles of potassium and iodine? Well, that's just going to be 1 and 1, because it's a 1-to-1 ratio between potassium iodide, potassium, and iodide. So now we know how many moles of each chemical, but also how many moles of each ion we started with. That's very important for later on. So what's the next thing we've got to do? Well, the next thing the question asks us to find is which is limiting and which is excess. So look at our net ionic equation here. It's clear that only lead and iodide are actually reacting. So they're the things we've got to worry about. And we can say that the ratio between lead and iodide is 1 to 2. For every 1 mole of lead ions, we need 2 iodide ions. And so looking here, we've got 0.0185 moles of lead ions. And for that to react, we need twice that much iodide to react with that. So we need 2 times that, or 0.163 moles of iodide ions to react. And it's quite clear that we need 0.163 moles of iodide. We've actually got a mole of iodide available. Therefore, the iodide is in excess and the lead is limiting. So this is a little visual to try and help you see what's going on. Here's our lead nitrate. The lead I've drawn as red ions, the nitrate as green, the potassium as blue, and the iodide as purple. And we mix these all together inside our solution. This is just before they've started precipitating. Now what we said was the lead was a limiting reagent, therefore the lead ions are all going to react, and they're going to react with some of the iodide ions in there, but we've got excess iodide. So once they've reacted, what's going to happen is all the lead is now going to be trapped inside the precipitate. Some of the iodide is now trapped in the precipitate, but there is going to be excess iodide. There are some extra iodide ions left over in the solution. The concentration of lead ions in the solution is now 0. There are lead ions here, but they're trapped in the precipitate. They're not in the solution, therefore their concentration in solution is 0. The iodide ions are still somewhere there, and if you look at the other ions, the nitrates and all the potassium ions, they've done nothing. So whatever the number of moles of potassium and nitrate there was in the original reaction, it's the same moles in the final reaction. So the two spectator ions, their number of moles stays the same in both solutions. The limiting ion is now gone to 0 because it's all in the precipitate, and it's the excess ion we've got to figure out the more complicated reaction, how much is actually left over in the solution. We'll get to that in the last part of this question. But first of all, the question asks to find the mass of precipitate. Now the mass of precipitate over here we just said was limited by how much lead ions there were in solution, because once the lead ions run out, the precipitate stops forming. And looking at the net ionic equation here, it's clear that for every 1 mole of lead ions, we end up with 1 mole of precipitate, because it's a 1-to-1 ratio. And therefore, if we look at this next slide here, that means the number of moles of lead ions is 0.0185, and therefore that's the moles of precipitate. We can calculate the mass, just number of moles times molar mass, gives us about 38 grams of precipitate. On to the last section. The last section now is the final concentration of ions. Now concentration is number of moles divided by volume, but this time the total volume is actually the volume of the whole solution. We mixed together a 2 litre and a 1 litre solution. Therefore the total volume is obviously going to be 3 litres. So the first thing, concentration of lead ions. We already said the concentration of lead ions is now 0 because all the lead is trapped in the precipitate. That's the limiting ion. Next thing, the nitrate ions and potassium ions. We started off with 0.163 moles of nitrate ions. We started off with 1 mole of potassium ions. As we said before, their number of moles doesn't change. It stays the same because none of them have actually reacted. So therefore, all we've got to do is take those number of moles, divide by 3, which is the volume, and get our 2 concentrations there for our nitrate and our potassium ions. The last thing, and the slightly tricky one, is what's the concentration of the iodide ions? When we talk about the concentration of iodide ions, it's the concentration of these ions that are still in solution. So we've got to find that final constant, or the final number of moles of iodide. And how do we find the moles of iodide? Well, it's however much iodide there was at the start. Take away how many ions are in the precipitate, or how many ions reacted. And we already know that because we said we had 1 mole of iodide at the start, and over here we said we know that 0.163 moles of iodide reacted with the lead. So therefore the final amount of the final amount of iodide in solution is just that 1, take away the 0.163, there are 0.837 moles of iodide left in solution, so therefore the concentration of iodide is 0.3 moles per litre. Now if you were pausing all the way through, I didn't really give you much time to pause, but if you were pausing all the way through and you follow that through and understand, great. If you're just watching though, now's the time to go back and see if you can solve this whole problem without looking, because if you can do that, that means you're one step closer to mastering limiting excess. Let's move on to the next question. This is question 6 from that worksheet A. I'm not doing question 5 because I sent an email through about question 5. So we're just looking at question 6 now. In this case, we've got 200 mils of a 0.15 mole per litre solution of iron sulfate react with 550 mils of a 0.55 mole per litre solution of sodium hydroxide. Calculate the mass of solid, concentration of sodium ions, and concentration of hydroxide ions. So it's going to be almost the same sort of question as before, just a few less things we would actually calculate. So first of all, equations. Well, there's our chemical equation, and there is our net ionic equation. I'm assuming now you know how to find those two things. The next thing is how many moles are we starting off with each chemical? I've already given this first one to you. Iron sulfate, just concentration times volume, or 0.2 by 0.15 gives us 0.03 moles of iron sulfate. We can break that into ions too. That means we can find the moles of iron ions and moles of sulfate ions. We don't really need the sulfate ions for this question. I'll just put it there for completion's sake. The next thing is the moles of sodium hydroxide we started with. Once again, concentration times volume equals to 0.3025, and the moles of sodium and hydroxide are the same as that because there's 1 sodium and 1 hydroxide inside sodium hydroxide. Next thing, what's limiting and what's excess? So we've got 0.03 moles of iron. For that, well, what do we need? Well, look at this equation here. For every 1 iron, we need 2 hydroxides. We need twice that much, or 2 times 0.03, or 0.06 moles of hydroxide is needed to react all the iron. So if we look now, we can clearly see that we've got 0.3025 moles of hydroxide available, which is much more than the 0.06 we needed to react the iron ions, and therefore the hydroxide ions are in excess and the iron 2 plus ions are our limiting reagent. On the next part of the question, what's the mass of precipitate? Well, the mass of the precipitate is limited by the iron ions because we said that was our limiting reagent. And it's clear from our equation here, our net ionic equation, that for every 1 mole of iron ions, we get 1 mole of precipitate of iron 2 hydroxide, and therefore the moles of iron 2 hydroxide is just that 0.03 we said we had for iron. Therefore, we can calculate the mass as just number of moles times the molar mass, which I'm sure you can do by now, which is about 3 grams to one significant figure. Last part of this question is the concentration of ions. We've only been asked for the concentration of sodium ions and hydroxide ions. Just for the record, we know the iron ions are limiting, and therefore their concentration will go to 0 because it'll all be used up. The sulfate ions are spectator ions in this situation, and therefore their number of moles will stay as 0.03. It's had to divide by the volume, but the question's not asking for that. We're looking for the sodium ions, hydroxide ions. So first thing is concentration of number of moles divided by volume. Well, what's the volume? We've got 200 mils mixed with 550 mils, so the total volume is 750 mils, or 0.75 litres. Sodium ions are spectator ions. That means whatever whatever number of moles we started with, that's the number of moles at the end. So we're going to still have this 0.3025 moles of sodium ions in solution. Divide that by the 0.75, gives us 0.4 moles per litre sodium ions left in the solution. The last one is the hydroxide. Now, hydroxide was our excess ion. Now, we know the number of moles of hydroxide at the end is how much we started with, take away how much reacted. Now, we know we started with 0.3025 moles of hydroxide. From this calculation here, we know 0.06 reacted with the iron ions, which leaves still 0.2425 moles of hydroxide ions floating around in solution. So what's their concentration? All we've got to do is divide that by the volume, which is 0.75, which gives us 0.3 moles per litre is our final concentration of hydroxide ions in solution. And that's the last 2 limiting excess explanations I can go through. Hopefully that'll help you. And once again, you don't know this actually until you've tried it by yourselves without any help. So you've seen this now, go away and try to do it by yourself. If you can get it right, that means you're one step closer to mastering limiting excess questions.